So welcome back to the next lecture of molecular spectroscopy. So due to some technical glitches, I have lost my recorded video. So I have shared some other video which is related with the dipole moment. Okay. So refer that video for the dipole moment introduction. Now the most important part for the spectroscopy is that for the given molecule there must be the dipole moment change and the polarizability in the given molecule. Okay, that the two important things that we have to consider in order to show the absorption for the particular radiation. So if we consider the IR spectroscopy or the visible spectroscopy, so there is the most important criteria is that that molecule should possess some dipole moment. Okay, so what do you mean by dipole moment and all that things are clear in that video. And for the Raman spectroscopy, the molecule must have the polarizability. Okay, so that are the two criteria that must be followed by the given molecule. And this dipole moment will increases with increase in the distance between the charges, then magnitude of charges, and if the molecule is possessing some kind of resonance, then also we can have the increasing in the amount of dipole moment for the given molecule. Okay, also we have seen the units for the dipole moment. Okay, so units for the dipole moment is dBi, which is named after the physical chemist, that is Peter dBi. Okay, so this symbol is represented by capital D. Also there are the other symbol like electrostatic units as well as some SI units are there. So for electrostatic units, what is the formula for this dipole moment? It is simply Q cross R, that is product of charge and distance. Okay, so consider the charge is being placed in the electrostatic unit and the bond length which is in the angstrom unit. Okay, so if an electronic charge of considered it is to be 4.8 into 10 raised to minus 10 electrostatic unit. Okay, it is the CGS unit. So it is assumed to be placed in the distance of 1 angstrom unit from an equal positive charges. Then the dipole moment of such a molecule, which is given by 4.8 into 10 raised to minus 10 electrostatic unit into 10 raised to minus 8 centimeter, which is comes out to be 4.8 into 10 raised to minus 18 electrostatic units centimeter. Okay, so the quantity which is 18 into 10 raised to 10 into 8, 10 raised to minus 18 is called as a 1 dBi unit, which is denoted by D. Okay, so we can say that this mu is equals to 4.8 dBi. Okay, so this is the one conversion. Also if we consider the SI unit, then for the SI units we are having charge as what? This is well known. Okay, for SI unit charge is 1.6 into 10 raised to minus 19 coulombs. Okay, this is coulombs, capital C. And R is what? 10 raised to minus 10 meter. If you consider the meter scale, then this R is 10 raised to minus 10 meter, because one angstrom unit is 10 raised to minus 10 meter. So now just simply multiplied by charge and this distance. So finally we will get again 1.6 into 10 raised to minus 29 coulombs meter. Okay, it is capital C here, it is not a small c, it is capital C. So this is coulombs meter. Okay, and now next is the this coulombs meter is equals to 4.8 dBi. So we just simply equate that, so we get another relation, that is 1 dBi is nothing but 3.336 into 10 raised to minus 30 coulombs meter. Okay, it is capital C meter. Okay, coulombs meter. So this is the unit for the dipole moment. Now next is the bond moment. So up to now we have seen the dipole moment. So dipole moment of a whole molecule is obtained. Okay, by experimental means we can obtain the dipole moment for the whole molecule. But for the molecule, like for single bonded molecule, like two atoms are involved in that molecule, so there is only one bond. So overall the bond moment and dipole moment of the molecule will be ultimately same. Okay, but in case of molecule which containing more than two bonds or more than one bonds, like methane, ethane, okay, likewise, so there the bond moment will resulted into the actual dipole moment of the molecule. So we will see the how does bond movement of one particular bond will affect the overall dipole moment of a given molecule. Okay, so any bond which has a degree of polarity, which has a certain dipole moment, so this is called as a bond moment. Okay, so this bond moment is representing what? The dipole moment of each bond. Okay, individual bond. So consider, if we consider this hydrogen hydrogen bond, so there is only one bond. So for one bond we can have the particular dipole moment of that particular bond, but here only one bond is there. So the overall dipole moment of molecule is again the dipole moment of this particular bond only. Okay, so here this hydrogen hydrogen is a non-polar molecule, so its bond is 0 because it is non-polar, so dipole moment of this molecule is comes out to be the 0. Okay, so bond moment is also equals to 0 and dipole moment is also equals to 0. Now consider next the HCl molecule, which is a polar molecule. So dipole moment of HCl bond is 1.08 dBi, which causes what? The change in the dipole moment of molecule because of its polar nature. Okay, so this is the simple. Okay, if we consider the two or the diatomic molecules, then it is quite simple to understand bond moment and dipole moment. So in diatomic molecule, the bond moment which is corresponds to the dipole moment of the molecule. So the dipole moment of halogen halides, which is shown in the below figure. So here we can see this hydrogen fluoride, which is having the highest electronegativity differences, shows the maximum dipole moment, then HCl, then HBr, and then hydrogen iodide. So here also you can see this arrow, size of this arrow is going to get decreased from HF to HI. Okay, because this arrow is showing the magnitude of electronegativity difference, that means magnitude of dipole moment in the given molecule. Okay? Now the bond moment will decreases with decreasing in the electronegativity of the halogen atom when the molecule containing more than one atom, more than two atoms, sorry, that is three or more atoms. Each bond has its own dipole moment. So consider like if we have like CH type of bonds, then it has the dipole moment of 0.4 dBi. If we are having carbon and chlorine bond, then it is having the dipole moment of 1.5 dBi. If we are having the hydrogen and oxygen bond, it is again 1.5 dBi. Hydrogen and nitrogen bond, it is 1.3 dBi. Okay, so in polyatomic molecules there are the number of bonds between the each atoms. So each bond which has its own definite dipole moment, and therefore it will make the definite contribution to the overall dipole moment of the molecule. Okay, and we have seen that this dipole moment is what? Dipole moment is a vector quantity. Okay, so due to the vector nature of this dipole moment, we have to consider the direction part also. So direction will be depending upon what? The angle. Okay, so if we know the angle between these two vectors, we can actually calculate the direction, and based upon the direction we can predict the dipole moment of the molecule. Okay, so we have to consider first the bond moment, and by based upon this bond moment we can actually find out the dipole moment of a molecule by knowing the angle between that two bond moments or the bond, simply because bond angle is known to us. So based upon that we can calculate the dipole moment of overall molecule. So how to find out that overall dipole moment? So there is one formula, like the dipole moment of a molecule is the resultant of the individual bond moment. So if mu1 and mu2s are the bond moments of the two bonds inclined at an angle of theta, then the resultant dipole moment of a given molecule is given by what? Which is mu is equals to under root of mu1 square plus mu2 square plus 2 mu1 mu2 into cos theta. Okay, so consider this. Suppose there are three atoms A, B and C, and if you want to find out the resultant dipole moment of a molecule, that is, this is the resultant dipole moment. So simply we just need to have the knowledge of bond moment of A and B, bond moment of A and C, and the angle of separation or the angle of that bond. Okay, that is theta. So if we get to know the three parameters, we can simply get the overall dipole moment of a molecule. Okay, so if the molecule is being symmetrical one and having the identical bonds, so its dipole moment comes out to be 0. Why is it so? Because this molecule, like consider, okay, we will see the example one by one. and again homonuclear diatomic molecules which are being non-polar, and they will show the zero dipole moment. Okay, so here we can see this various bond moments. Okay, so individual bond moments are calculated experimentally, and these are explained in this table. Okay, so here lots of values are given for the each bond moments, like for HF, HCl, HBr. Okay, then carbon oxygen bond, that is zero point 0.7, carbon hydrogen which is zero point 0.4, carbon carbon 0, carbon fluorine it is 1.4, carbon chlorine it is 1.5, for CBr bond it is 1.4, CI bond it is 1.2, and last carbon oxygen double bond which is 2.3. Okay, dBi, all the units are in the dBi. So consider now the specific examples. So now consider the ortho substituted benzene. Okay, ortho disubstituted benzene. So suppose the angle between the bond moments mu1 and mu2 of the two substituent, that is x and y, is around 60 degrees in the benzene. So we can now calculate the dipole moment of molecule, which is given by what, the formula, that is mu1 square plus mu2 square plus 2 mu1 mu2 into cos theta. So let us consider that the two substituents are identical, so that what happen, so due to the identical nature of the substituent, we just simply have the bond moment of first substituent equals to the bond moment of second substituent. So for mu1 is equals to mu2, we just simply need to substitute into the dipole moment formula, that is mu is equals to under root of 2 mu1 square plus 2 mu1 square into cos of 60, which is comes out to be mu into under root of 3. Okay, if we have the equal or the same substituent, that is ortho disubstituted benzene with same substituent. So the dipole moment of ortho dichlorobenzene, because we know the chlorine and carbon bond moment. Okay, so based upon that, we can have the value of this chlorine and carbon bond as 1.5 dBi. So overall we can see that the ortho disubstituted benzene shows the dipole moment of 2.598 dBi. Okay, but there is a experimentally we can observe the less dipole moment. There is a certain reason. Okay, so in ortho substituted disubstituted compound, the observed dipole moments are always less than the expected values. Okay, this is the important observation that we have made experimentally. So why is it so? Because the repulsion between the two substituent group causes the slight deviation from their actual position. Okay, so due to the repulsion, we can get the decreasing in the dipole moment that we are expecting based upon this formula. Okay, or based upon this calculation. So as a result, the angle between the uh, these two substituent becomes more than 60 degree, and hence the dipole moment get decreases. Okay, so for example, this ortho nitro dinitrobenzene, the observed dipole moment is 6 dBi, but the expected value is around 6.9 dBi. So there is a difference of around 0.9 dBi. Okay, so that is for the ortho case, and here we have observed that the calculated values are always greater than the experimental values. Okay, so now consider the meta substituted compounds. So in meta substituted compounds, the angle between the bond moments mu1 and mu2, which is comes out to be what, which is 120 degree. Okay, meta substituted benzene. Now the dipole moment of molecule, which is given by again that same formula, that is mu1 square plus mu2 square plus 2 mu1 mu2 into cos of 120. Okay, these are all 120 is what the angle between the two meta substituted substituent. So if we again consider the two substituents are being identical or equal, then mu1 is equals to mu2. Okay, that is the bond moment of two substituents are equal. So this mu is equals to become 2 mu1 square plus 2 mu1 square into cos of 120. So now just simply substitute here, and finally we'll get the value of around 1. Okay, so simply it is the molecule is being symmetrical and having the identical bonds, its dipole moment is comes out to be 0 because of the individual bond moments which will cancel each other. So various bond moments or the dipole moments are given in the previous table, that is 5.20. Okay, so that is the dipole moment and bond moment importance. Okay, now we will try to see the dipole moment, relationship between dipole moment and the structure of the given molecule. Okay, so based upon the dipole moment, how can we actually predict the structure of given molecule, that we can see in the upcoming lectures. Okay, so there are the quite few examples where we can actually predict the its structure. Okay, so with that we can see that in the next lecture.